Okay, let's go ahead and start. This is Jim Ledoux, and I'm happy to introduce Bryan Smith, Chris Karstens as speakers for this webinar. And the title there, as you can see, the preliminary evaluation of a real-time diagnostic tornado damage intensity estimation tool used at the Storm Prediction Center. This is the first of several webinars that are going to be somewhat related to the users of the Weather Service's storm data information and also that of the Damage Assessment Toolkit. And they spread across varieties of sectors, including Weather Service, and this is, of course, an example, but also we'll be introducing speakers that are using this kind of information from academic sectors as well as other federal sectors.
Thanks, Jim, for the introduction. Certainly want to thank WDTD and just acknowledge the others that were a part of this work, and that it would not have been possible without them included. I guess I just have a story sort of to share with everybody to start off. Sort of once upon a time, Weather Service forecaster, sort of with little experience that started out here at the Storm Prediction Center in terms of tornado intensity forecasting. And just a little aside, this forecaster's passion was instead in the fire weather forecasting arena. He was able to use the information that I'm going to present here today to correctly describe in an explicit manner tornado damage intensity using a wind speed range. And so you may ask, well, Bryan, can we use explicit tornado damage intensity and do it skillfully? And I'm going to present some evidence that I believe is pretty compelling today, and this will be followed up by work Chris has spearheaded in which a tornado damage model can be run post-tornado and give meteorologists, as part of their IDSS mission, an ability to provide pretty good first guess damage information to Weather Service Corps partners as to where the most intense damage and magnitude of the damage may be located. So I just sort of want to share a screen, and this is what the DAT looks like. This is the Mayfield, Kentucky tornado from last December, a series of 2 F4s there, and we think we have a secret to share with you today. The real-world application of the tornado survey data, basically the last 5 years we've been looking at this information and try and develop a pretty statistically rigorous technique from which we data mine the DAT information. And basically, can we look at past tornado data to tell us about what may be ongoing in terms of tornado intensity? And so with the DAT, there's certainly an importance for having high-quality tornado data from which we can then build pretty good scientific data sets and use this meteorological forensic sort of techniques to build these tools and basically schemes in which we can say something about what's going on in real time. And finally, just want to mention that we don't necessarily know what truth is in terms of actual tornado intensity. We're using damage to make assumptions, estimations, and certainly not everything is necessarily complete in terms of a tornado damage field in terms of being able to reveal peak damage at any particular instant. But with that said, we do know that tornado forecasting and particularly intensity is a difficult problem to tackle. And so we took basically sort of techniques from other hazards like hurricanes, in which there's a wind speed assigned to a hurricane 500 miles out into the Gulf, where we're using basically remote sensing to come up with a maximum sustained wind speed for a hurricane. Likewise, for hail algorithms, we have explicit hail sizes in our Weather Service warnings from which we build IBW off of, impact-based warnings and the associated IBW information from that. The idea with this was, well, can we build a foundational layer of explicit information to help layer IBW tornado warning information on top of, so we can have a little bit more rigorous technique at assigning IBW. And so this is a web-based tool that was developed here at SPC a couple of years ago by Matt Mosher, and I'll just go over this. We're basically sort of taking two parameters, rotational velocity, what we'd see from a single site 88D, and the significant tornado parameter, and binning these values. In this particular case, we took a rotational velocity, or VROT, and STP 60 to 69 knots and a 3 to 4 STP, and this gives you an output wind speed range of 100 120 to 165 miles an hour. And we also have a time component as well. And so I'm going to sort of go back and forth between sort of an instantaneous look at damage intensity as well as sort of a cumulative look at peak tornado damage intensity, how you would necessarily assign a peak tornado damage rating and its associated wind speed. So you can see with this graph, it's just sort of this nice 2D plot of STP there on the x-axis and then VROT on the y. And we're able to find this pretty nice relationship in terms of damage intensity using wind speeds. And this is all based from the DAT data, which comes from this particular web page, brings in information from thousands of tornadoes and many different volume scans of information. And so with this data set that we developed, we wanted to test, well, how well does this do with an independent data set? And so we looked at 99 tornadoes that had a tornadic debris signature, meaning showing up as a dual pole signature on the 88D. And these were all events within, say, 100 statute miles of the radar. And when they had a TDS, what was the wind speed with that particular tornado? And so we matched up the peak damage indicator wind speed in the vicinity of a circulation, a tornadic circulation, and time and space, and assigned that particular half-degree scan as a half-degree DI or damage indicator scan. And we had 765 of these scans from 99 tornadoes that spanned from the fall of 2020 to the spring of 2022. And so here's just the spatial distribution of these events. And so this is based on the damage that was revealed at the ground for these particular tornadoes, the wind speeds. So with this data set, here's just a bar chart of the 765 scans. Most of these scans were F1, F2, but we also had some F3 and even F4 damage indicator scans. So from these 99 tornadoes, again, this is 765 points along the path of a tornado in which this is the wind speeds associated at the ground with those scans based on damage. There's sort of two techniques, an instantaneous look at what's the damage going on right now, and then what is the peak damage wind speed associated with the final rating of these 99 tornadoes. And we have a technique in which we bring in time information to help us with that. So if you have a circulation going through a debris field, generally the more amount of time that you have, the higher the probability that you're going to reveal the peak damage intensity associated with that circulation. So with this chart, this is just the 99 tornadoes and their peak wind speed associated with their final EF rating. And so again, most of these were F1, F2s, F3s, and some F4s during this year and a half study period. And so going back to the what we'll refer to as a per scan or the instantaneous method of these half-degree scans, most of these, an overwhelming majority, were within, say, 60 or so miles, statute miles of the radar, or less than 6,000 feet ARL, denoted here with most of these over here on the left two-thirds of the plot, although we do have a couple at pretty far range. But this technique's really only applicable within 100 miles or 10,000 feet or less ARL height. And so this is a sort of busy plot, so I'm going to take you from left to right with it. So beginning over there on figure A, this is basically a distribution, and so we're predicting a wind speed range with this technique. So in this particular example, we'll use, say, a combination of VROT and STP gives us a 100 to 140 mile an hour range. And if the damage at that point along the path of the tornado fell within that 100 to 140 mile an hour range, that would result in a 0 mile an hour air, or in this case, you can see there 66% of those fell within a predicted wind speed range. We then noticed that with this sort of instantaneous or per scan method, it tended to have just an ever so slight overestimate bias based on what was actually observed based on damage at the ground. So if we had a predicted wind speed range of 100 to 140 and you had damage verifying at the ground of 95 miles an hour, which would be lower end F1, you would fall within this 0 to positive 10 mile an hour overestimate bin right here. Basically, if you made a larger wind speed range, you would actually capture 80 to 85% roughly of the peak damage indicator within that wind speed range, whereas if you made it too small, you would have sort of less skill, you would capture less than 66%. So it's sort of a Goldilocks to where you don't want to make the wind speed range too large to where it's not very useful, but not too small to where it's not statistically reliable and useful as well. So the green plot over there is an instantaneous sort of look how a weather service forecaster at any given moment looking at radar data and environmental information would be able to assess damage intensity. The plot over on the right is the per tornado example, or how you would look at it from a cumulative sense, and this is sort of how the Weather Service, we think, uses IBW in practice in terms of assigning sort of like, I'm going to give a catastrophic tag or a considerable tag for this particular tornado event, and it may or may not be necessarily revealing catastrophic damage at the ground, but maybe in 5 minutes it is, or it's sort of in between damage indicators. So with this per tornado example of adding in a time component, you get a damage wind speed range of 120 to 160. So again, if it fell within that wind speed range, you'd have a 0 mile an hour air. And based on our data set of 99 tornadoes, we found that some of them had a slight underestimate bias, but again, the majority of them fell within that wind speed range. So if you had a verifying wind speed at 165, which would be upper end F3, and you had a predicted of 120 to 160, it would be 5 mile an hour underestimate, and that would fall in this bin right here. And so you can kind of think of this information in terms of its performance as analogous to tropical cyclone track forecast cones that NHC provides, where they're basically based on a climatology using a 2/3 probability ellipse. And if, again, like I said, if you increase the wind speed range, you're going to even have higher, basically 80 to 85% are within the wind speed range. So I'm going to take this information right here and plot it in the performance diagrams and a 2x2 contingency table. So if you have a 0 mile an hour air with your wind speed range, that's considered a hit. The misses, which would be an under forecast, and the false alarms, meaning an over forecast, and plot this in a performance diagram. And this is where you would find this information in the upper right part of the diagram, which POD is very high. The success ratio, which is the inverse of the false alarm, is very good. And the CSI values there you can see 0.66 and 0.687, which is very, very good. So here's just a spatial distribution of these events and how they fell within or an overestimate or underestimate in terms of how they performed. You can see the longer track tornadoes like Mayfield that fell within the wind speed range, as well as several other pretty longer track tornadoes. Did notice that there was like a tornado in the Texas Panhandle that was a overestimate. That happened to be like a 90-some knot rotational velocity and a moderate risk tornado outbreak, and it just didn't hit that much. And so we're also including some of those types of events in this data set as well. So finally, just wanted to sort of compare how the Weather Service looked at the Weather Service peak tornado warning tag versus the technique that we have that's using a base value of 110 for considerable, or a lower bound wind speed of 140 for catastrophic. And they're pretty similar distributions to one another, although we did find that the technique that we developed here sort of helps redistribute some of these underperformers that would be in the catastrophic and put those in the no IBW tag or the considerable tag distribution. So that was a good finding there. And then finally, this technique's been recently evaluated at OPG this past summer, where they looked at it from a per scan method. And we have heard that some weather service offices are starting to use this technique, specifically the Salado, Texas EF3 back in the spring. And we've been looking at this routinely to sort of help internally diagnose tornado damage intensity for the last couple of years. There's a QR code in the upper right where you can actually download the web-based tool. It's just some simple HTML, basically a simple web page that you can look at. And here's just an example of from a couple of years ago with one of my former colleagues that explicitly provided some tornado damage intensity estimate of the So-So Bassfield, Mississippi EF4 event. So with that, I'll pass it along to Chris.
Thanks, Brian. So yeah, I'll just shift gears here a little bit and start talking a little bit about how this method can be applied in a post hoc sense and really kind of an immediate post hoc sense. As we know, as natural disasters occur, the areas that are impacted are not immediately obvious or well known. And then within those areas, the magnitude of the damage especially is not very well understood. And the method that we use to do that, of course, is just with the post-event survey, which can take days, weeks, and even sometimes months to really ascertain the full picture of what occurred. Meanwhile, the emergency management community, they're tasked with the first response, and then thereafter has come to resource allocation. When you have an event like was pictured here, more in 2013, this will activate every level of emergency management community there is, so local, regional, and national level. And certainly this type of event, is rare. It's kind of a career event and will overwhelm these services pretty quickly. And obviously when it happens in a metropolitan area, the potential for significant damage and loss of life is probably relatively high. So this is the EF scale damage contours from the DAT from this event, the Moore tornado event in 2013. And I just wanted to give this as an indication of the detail of the damage survey here. This is probably one of the most, if not the most, detailed damage surveys that's in the DAT. There's probably on the order of around 5,000 DIs for this one event in the DAT, and it took a multi-agency effort really to pull this off as well. So, but you can just see really the reality of the situation here and just the extent of damage that occurred here across a major metropolitan area. And if we zoom into the west side of I-35, the triangles here show you the DI points again, and you can see several hundred, if not probably a few thousand here just on this in this one part of the track. Very densely populated area of the track, and of course, unfortunately, we had fatalities occur here. So again, just kind of underscores the points made on the previous slide. Okay, so the idea is, can we use this information, that Brian described in an immediate post hoc sense? And so the idea is, instead of, just using it on a scan here or there along the track, or, just using it in a cumulative sense like Brian described, actually just use this on every single scan that you have available along the tornado track. What's pictured in the lower left are the empirical distributions that underlie the tool that Matt Mosier developed. There you see all of the uncertainty within these various portions of the parameter space. And so the idea is, can we take that information and then marry it with, an ongoing effort in the Weather Service to provide preliminary tornado tracks you see in the lower left. It's based on a method developed by Spager Smith in 2006. Those tracks really just give you a depiction of where the tornado might have occurred, and currently don't really give you an indication of any variation in intensity along the track. And so what we can do potentially is fill that in with information from these empirical distributions. And to do that, I use some help from an analytical vortex model that was part of my PhD work here, you see on the right side. Okay, so just in a proof of concept mode here, the first thing was, can we do this? And this was sort of a depiction of the first attempt at this. And here we're extracting wind speed values from the middle portion of the distributions, from the empirical distribution. So doing that, we're getting, what might be considered like a most likely type scenario here. And in this case, it does depict, EF4 damage. You see variation intensity along the track. And if you kind of take a mental snapshot of this and then go to the next slide, there we see the reasonable correspondence, spatially, as well as, just orthogonally along the track with depictions of where the most intense damage occurred. So this kind of gave us a little bit of confidence to say, okay, hey, yeah, maybe this is something we can pursue a little bit further. Of course, again, what you see here takes, days, weeks, if not months to create, whereas the preliminary tracks can take on the order of minutes to create. And here you see if we extract values from the upper percentiles from the distributions, you can obviously then get higher wind speed values. So this gives you, perhaps a worst case scenario. And then next slide shows lower percentile values. So perhaps, more of a best case scenario if the tornado doesn't happen to encounter, really any damage indicators that reveal those peak wind speeds. Okay, so the idea is to take this model, the statistical model, and apply it to the same data set that Bryan described. It actually includes a few additional tornadoes beyond those with TDSs explicitly. So 115 tornadoes, use 6,425 damage indicators from the DAT as the verification data set. Same assumptions and limitations that Bryan described apply here regarding the DI wind speed and its relationship to the peak wind speed of the ground. And then I evaluated this within a few radii of the DI itself. So 0 meters, at the DI location, 500 meters and 1,000 meters of the point. And I created 101 percentile based tracks. So just extracting consistent percentile wind speeds based on the VROT, STP, and population combinations. The plot in the lower right shows the error distributions that result from this. And kind of the good result here is you see the lower percentile values on the left side have a low bias, kind of under prediction of the wind speeds, whereas on the right side, the upper percentiles kind of overdo it. And then in the middle, you see better correspondence, distributions that center on 0. Interestingly enough, kind of where they center on 0 ends up being closer to the upper percentile tracks, in this case around 90th percentile. The interquartile range, though, is fairly confined. So it's within, plus or minus 1 EF scale range approximately. So, about 50% of the time at the DI location, we're able to depict what essentially the wind speed is within a reasonable range. And then one other metric I looked at was reliability. In this case, looking at the variability and the reliability using these box of whiskers and violin plots on the right side there. And I grouped those by the EF wind speed ranges as well. So what we see as you look at all three of those plots is just a very strong linear bias. You don't see a lot of gradation like you'd like to see in a reliability plot. And I think what this really just indicates is just, again, you're cross-cutting through the percentiles, so you're kind of getting consistent wind speeds from the distributions. But with that, then, so no one track is really able to fully give you the variation in intensity that you see at the ground. But if you use a combination of different percentiles from those distributions, then you can get a little bit better depiction of what the lower bound, the upper bound, and something in the middle might look like. So in this case, what fell out was the 50th percentile kind of gives you a pretty good indication of what EF0, EF winds might end up looking like if that's what ends up being revealed at ground level, whereas the 75th percentile was closer to the EF2, EF3 range, and then the 97th percentile gives you a better depiction of the EF3, EF4 type event. So again, kind of lining up with that idea of using kind of a best case, worst case, most likely scenario type of a methodology. These are just 3 examples from the independent data set just to give you kind of a visual depiction of what this looked like. So upper left is that best case scenario, 50th percentile track is contoured. Again, using EF scale levels here on the scale, and then the triangles are the DI points for this event. And so in this case, the tornado didn't hit a lot, so you see it actually end up being pretty good correspondence for a best case type scenario. Upper right, most likely scenario, again, good correspondence there. And really in this one, the tornado intensified in that middle part of the track, and you see that depicted and ended up seeing damage indicators that reveal that as well. So that's kind of a good case there for it. And then the bottom right is that worst case scenario. There's kind of a metropolitan area in the middle part of the track, and that's where we see EF4 DIs that ended up occurring and revealing peak wind speeds. But, in the more desolate parts of the track, even though the tornado statistically from the distributions suggests, may have been intense, it just didn't really hit anything, so wasn't able to really reveal the peak wind speeds, but certainly could have been an intense tornado in those parts of the track. Okay, so finally, just to touch on kind of the future from just the analysis here, the verification, we're looking at the verifying distance. So even though we have the strong linear bias from the output and the reliability, the model is actually able to depict the verifying wind speed within some radius of that DI point. So the question is, how far away is that? And what does that variability look like? And that might then inform more of a probabilistic depiction of the intensity. So like what you see here in this animation. The question is, what radius of influence do you use? And so using that verifying distance from these 115 tornado events, I think should help us with that. And then just lastly is just summarize all these results and publish those. And this was presented at the AMS SLS conference here last month. And so just to kind of plug that, there is an extended abstract to peruse if you have the time. So, but we'll be hopefully adding to those results here in the near future. That's all I got.
All right. Well, thank you, Bryan and Chris, for that presentation.